Today we are going to discuss transfer function analysis. First one, we discuss characterization of a Lrti system. Characterization Lrti system. Before we mentioned, we have several methods to describe a Lrti system. The first one is we can have a difference equation. The next one, we can have an impulse response. Today we are going to focus on system function or transfer function. So let's review the first one, the impulse response. Everybody still remember what impulse response is? For a discrete system, what is the impulse response? That is the response or the output of the system when the input is an impulse. The second method is called system function. Or we can call this a transfer function. A system function actually is just the z transform of the impulse response. And we write the impulse response as hn because this is in time. So little small h and as function for time n. And this one will be the z transform of hn, which is a capital H and as a function for z. And this square, this is just the parenthesis. The next one is called linear constant coefficient difference equation. And if some conditions are met, these three descriptions are equivalent. We are going to discuss or mention later time what the condition is. We have example, the impulse response. Assume the impulse response is Hn equals B0 A to the n Un plus B1 A to the power for n minus 1 and U n minus 1. You can imagine if the input is just the impulse to the system, then the output of the system will be B0, which is a constant, A is constant to the power of n, Un, unit step function, and plus B1, another constant, A to the power of n minus 1, then with delayed by one time unit step. So this is the impulse response. Then, how to calculate the output for a signal? For example, if the signal equals xn, just the arbitrary input signal, how to calculate the output of the system? We mentioned this in previous chapters and we know how to do that. So the output, which is a function of time, yn, is related to the xn and the impulse response by operation. What is that? Convolution. So convolution is represented by star. And we know for discrete system, discrete signals, the calculation of convolution is relatively easy compared to analog signal. So this is now we may ask how to find the impulse response if I give you a system. You just input the input terminal with the impulse just 1 when time equals 0, then you measure the output. For discrete system, it's very easy. Just calculate. You just measure what is the output when time equals 0, what is the output when time equals 1, equals 2, and so on. So you just record all these discrete values, then that will be the impulse response of the system. This. The second one example is for system function. As we said, system function or transfer function is just the z transform of the impulse response Hn. Whereas if we know the impulse, the system function to a system, how to calculate the output, and we discussed this also in previous chapters. So anybody still remember this? If we know the system function, which is obtained from the z transform of the impulse response. So how to calculate? I'll give you also give you an input. How to calculate the output? Step one is we calculate the z transform of the input, which is represented by capital X, z, and we are given the system function. Then what is the operation here? Instead of convolution, it will be just ordinary multiplication. Okay, we multiply these two. What we have here is the z transform of the output. We need the time domain output. So from here, we can take the inverse z transform. We can get the time domain output. So this is if we are given the system function, then we can calculate the output of the system by this method, z transform and the inverse z transform. Alright, the third example is if the system is given by linear constant coefficient difference equation. For example, yn minus a yn minus 1 and equals b0 xn plus b1 xn minus 1. Here a, b0, b1, all these three are constant. So it's called a constant coefficient. And this is the linear system and the difference equation. So how to calculate the output yn if we are given initial conditions of the output and also the input signal xn? How to do this? We discussed this before also with two methods so far. Anyone still remember that? What's the first one? Recursive method, right? The second one is we convert this one, take the z transform of both sides of the difference equation, then we try to find the yz, then we take the inverse z transform. So all these three method descriptions are for the equivalent, right? In some sense, for the system. So I hope everybody understand all these three methods before we discuss the example. Okay, next we are going to use an example to show how to analyze the system. The first one is first order transfer function representation. First order transfer function representation. For first order transfer function, that means we have if you look at here, if we are looking at the difference equation, this time equals n. This time is n minus 1. So the highest is n, the lowest is n minus 1. The difference between these two is only 1. So that is called first order. If this one is n, we have this, then we may have another one minus c y n minus, for example, 5. what is the order of this difference equation of this system? It's fifth order. The reason is the highest equals n, the lowest is n minus 5. The difference between these two times is n minus 5, which equals 5. So this fifth order. Right? So for first order system, we can only have n and n minus 1. Right? So we have an example here. So yn plus a constant yn minus 1 equals the input, and that's very simple, just multiply by constant b. So we are going to see what is the output, or what are the, we are going to analyze this system. We use the method we discussed before, use the z-transform method. Right? So we take the z-transform on both sides. What is this? Take the z-transform of this. What is this? yz, right? Okay, this one here, we use the linear property, so there's a constant a here. Then take the z-transform of yn minus 1, which is z to the negative 1. We mentioned it before. n minus 1 deleted in one time corresponds to, in frequency domain, z to the negative 1. So that's why we prefer use z to the negative 1 instead of z in the z transform and the inverse z transform. Right? So z to the negative 1, there's yz here, right? Because this is for yz signal. And if we have initial condition, then we need to minus little y, that corresponds to this, and negative 1 here. So this is the initial condition. If the system is initially at rest, then this just equal to 0. Then, okay, we don't have any terms on the left-hand side. The right-hand side will be a constant b, then times xz. Right? Then we try to solve yz. So we have this term here. So we have 1 plus az to the negative 1 on the left-hand side. And we move this term, we leave this term on the right-hand side and move this times this on to the right-hand side. Then we solve yz will be equal to, first one we consider this constant. This constant is so a y negative 1 move to the right, then divided by 1 here plus a z to the negative 1. Does this make sense? Okay. Then don't forget this term. So plus there's b here, and again we have this coefficient 1 plus a z to negative 1, and then times this. I think we have mistake here. This is supposed to be plus, and this is supposed to be move this one to the minus. Okay. Okay. Any questions so far? Okay. The next step is very straightforward. We just take the inverse z transform, then we can find the output. Okay. Now before that we want to discuss. In the output we have two terms. This one and this one. Remember we mentioned before, we have a zero input response and zero state response. What is this? Where does this term come from? It's from this initial condition. That means this term is the output when the input equal to 0. If the input equals 0, this is gone, then we have this one. So this is called a zero input response. So we call this a zero input response. Means the input, when the input equals 0, that is the output of the system. Totally due to the initial condition. Okay? Then what is this? This is only due to the input. So that means the initial condition must be equal to 0. So this is called a zero state response. Right? So the complete, this then add up together, we call this a complete response. So the complete response of the system is the sum of the zero input response and the zero state response. Right? We need to be able to distinguish between these two responses, and the sum of the both equals the complete response. Okay, now let's. This is a general first order transfer function. Right? Now we make this. Give it this example. Suppose the input is assume input is just the unit step. Right? Or we can ask, what is the unit step response of the system? That means the input is a unit step. Right? Even I don't tell you. If I just said, what is the unit step response, you know this xn will be un. Right? So what is this? Okay, from here we know xz will be, what is the z transform of a unit step? Memorize this. Right? So that one will be equals 1 over 1 minus z to the negative 1. Now we plug this term into here, and we can find then we have yz equals we assume the zero initial condition, right? We have another one. Initial condition. So zero initial, the system is initially at rest. So we assume this term equals 0. Right? Then this one will be b1 plus az to the negative 1 times 1 minus z to the negative 1. It's 1 on the top. How to do next? We are looking for the time domain response. So we need to take the inverse z transform. Right? We are given this z transform. How to do that? We need to use what technique? Partial fraction expansion? Yes? Alright. Good news is the root here equals negative a. This one equals 1. So hopefully, suppose a is not equal to 1. Right? We make an assumption a not equal to 1. So this one will be unique. Right? Then we can we will have 1 plus a z to the negative 1, constant a on the top. Then plus 1 minus z to the negative 1, constant b on the top. Do you still remember how to calculate a and b? Right? I don't bother you here how to do this. You should be able to do this. Okay. So anyway. Once we do this, that one will be equal to AB and A plus 1 and 1 plus A z to the negative 1. So that means capital A, constant capital A equals this one. Right? Then plus and capital B, constant capital B equals B over A plus 1 and 1 minus Z to the negative 1 on the bottom. Right, so yn will be equal to, and use linear property. So this part will be A plus 1. Still remember what's the inverse z transform for this? Looks like this is exponential, right? Alright, so that will be equals negative a to the n and un. Okay, I will put leave the un at the very end. Then plus this term, this is un, So it's B, A plus 1. Does that make sense? Okay, now, together, so UN. I want to combine these two terms because it looks like they have a common terms. This here. So I will make this one A plus 1 and move this A inside here. So leave B outside so that we have a common term, a common coefficient, B over A plus 1. Then this term will be multiplied by A to here. But there's negative here, there's no negative here. If we have negative this here, then that's easy, just negative A to the N. But we don't have that one. So it will be negative A and N, original N, then we have another one, so that will be N plus 1. So this is this term, then plus what? This part is done, right? Okay, so this part, we move this coefficient outside, so then this is fine. U. So this is if the system is initially at rest, and this is the output to the input, or the unit step response. So this is also called the zero state response. Question on this? It's good? If in the homework or anywhere I give you, for example, give you an initial condition, then what you do is you can combine these two terms together from here, then find the complete response at once. Or you can break this into two terms, find this first, which is zero input, then find this second, this is zero state. Then you add up these two together, we get the complete response. Maybe the second way is better. Usually I will ask you what is the zero state response, what's the zero input response, then what is the complete response. If you still remember in ECET323 or somewhere, okay, analog, we are going to, when we discuss second order circuit, we also have this kind of concept, zero state response and zero input response, then complete response. And this is exactly the same concept. Okay, any question for this? The next one will be a second order transfer function. Example 2, so we put this one example 1. Example 2, second. Second order system. Again, transfer function. So we assume a causal linear time invariant discrete system is given by difference equation yn plus a1 yn minus 1. Up to this point, that is only the first order system. So we need to have an additional term, which is a2 yn minus can only be 2, right? Cannot be 3, cannot be 4, right? Can only be 2 because this is the second order. So n, the difference between n, highest order, and the lowest order is 2, so that's the second order. That's it, on the left hand side. On the right hand side, we have b0, then times xn, so that is just the linear combination of the input, then plus b1 xn minus 1. Okay, so that we have two terms. This is the original input, this is the delayed version of the input. The difference between here and here, or we have more, is not the order of the system. So that means if we can put the n minus 10 here, doesn't matter. Does not affect the order of the system because this is the input. So for here, we just put make it simple. We have only two terms. Okay, so how to analyze this system? You should be able to do this by yourself. At least you have the idea, right? How to do this? Step 1. Take what? On both sides. Z transform. Alright, so let's see this. This one will be Y, Z, right? And then this one here, so A1 constant, and here -1. What is it? Z to the -1 and YZ, then plus Y -1. This is the initial condition. So that's it for this term. And for this term is A2. What is this? Z to the -2, right? Z to the -2 and YZ, then plus what next? Alright, and Y -2 plus Z to -1 and Y. Okay, we put constant before that. Then Y -1 and Z to -1. All these transforms are in the table, so you need to better memorize this because those are very common. We use this a lot of times, or at least you know where to find them. So those terms are the Z transforms of the left-hand side. Then to the right-hand side, so B0, XZ, then plus B1, XZ, and there's a Z to the -1, then plus X0. Any questions? All right. What's next? Find solve for YZ, right? All right. So YZ, capital Y, will be equal to. Alright, so this coefficient equals 1. This coefficient equals A1 Z to the -1. And there's another one here, A2 Z to the -2. So we need to collect all these terms together. Right? And all other constant terms here, will move to the right-hand side. And this due to the input. Right? We can make this system, okay, so this one equals 0. Right? That doesn't matter because if we are given the input, then we can easily calculate the Z transform. Make this simple, we assume that term is gone. Right? So we have only this. Okay, so now YZ equals, the coefficient is 1 plus, so 1 plus A1 Z to the -1 plus what? A2 Z to the -2. And we do the zero input term first. Zero input means we only count the initial conditions. What is on the top? Negative A1 times this, right? So negative A1, Y, -1. What's the next term? This one, right? And this one. So that will be A2 minus, okay, I put all this together, so that's plus A2 y negative 2, then plus A2 y negative 1 and z to the negative 1. So everything good? Okay, then what is on the right? The next term. This is the same here? Yes. So 1 plus a1 z to the negative 1 plus a2 and z to the negative 2. What is here? B0 plus. Everybody look at this. You have time to study the slide after the class. Now everybody follow this. What is on the top? B0, right? Then plus B1z to the negative 1. Yes? Right, plus B1 z to the negative 1. And here we are going to have x z. Okay, what is this? What we call this term? Zero input response. And this one is a zero state response. Add up together, we call this complete response. Right? This system is initially at rest because we ignored the input x. Okay, right? So okay, so now, so suppose okay, I'll take this back. Okay, so if the system is initially at rest, means no output. That means all this term, all these terms are equal to 0. Then the transfer function is defined by the output over the input. The z transform of the output over the z transform of the input. Right? If this term is gone, then yz over xz will be equal to just this part. Right? So this one will be equal to 1 plus a1 z negative 1 plus a2 z to the negative 2. And this b0 plus b1. So this is the system function. If we take the inverse z transform, then this gives us the impulse response. Right? Now, if you compare this transfer function with this difference equation, all the information is here. Look at this. A1, A2, B0, B1, all are here. Right? And this one is minus 1, so that corresponds to this minus 1 here. Minus 2 corresponds to minus 2 here. And this one, deleted by 1 time is this, and no delete, just equal to this. So that's why we said this linear constant coefficient difference equation is equivalent to the system function with some condition. What condition? Okay, initially at rest, then we can ignore this term, then they are equivalent. So this is give you a way to calculate the system function or transfer function if we are given a difference equation. You just ignore all the initial conditions, then just like this. So now what I want is, if you look at this difference equation, and you look at this, you need to convince yourself these two are equivalent. Because the following lectures we are going to, no matter give you this, you need to be able to, okay, this one is that. Does it make sense? So look at this again. Okay, now you believe they are equivalent, right? Okay, so now for example, I'll give you a yn plus 2 yn minus 3 equals xn. What is the transfer function for this? What is actually? You need to write out this one instantly. Or you cannot, right? Okay, now look at this again. Well, this is 1 here. Where does this 1 come from? Yn, right? So remember at the very beginning when we said we discussed difference equation or differential equation, we always put this 1 here, so scale to 1. If I do not, this is not given as 1, you divide by the coefficient. So this one always equal to 1. Right? So 1 is here, then A1 is here, and A2 is here. So you just, all those are the coefficient of the output or the left hand side. And this one corresponding to n minus 1, this one corresponds to n minus 2. And on the top, B0, B1 here, and this one, no delay, this one delayed by 1 time. So it's very clear, right? Okay, so now tell me what is the transfer function here? Okay, 1, why this is 1? Okay, because that is B0 here, right? On the bottom, 1, right? Plus 2 to what? Z to the negative louder.
3.
Okay, negative 3, good. Right? Very easy, right? Alright, from here to here, it's a little bit easier. Now go back. Alright, I'll give you this one. Can you write out the difference equation? We know it's already here, but it's gone. You still memorize, right? So that means this one is yn plus 2 yn minus 3 equals what's this? Xn. Or easier way to memorize is this one xz actually is defined by yz or xz, right? This is better. Now cross product. This equals this, right? Okay, so yz times 1 means yz. You take the inverse z transform, this gives us yn. And this one, 2yz and z to negative 3, we mentioned z to negative 3 means delayed by 3 times. 3 seconds, right? So this one is 2yn minus 3. And equal to xz, this one inverse, just xn. Does that make sense? Right. If I change this one to z to negative 1, left hand side is still the same. The right hand side equals what? Xn minus 1. Make sense? Everybody? You are comfortable with this? You need to, otherwise you are going to spend a lot of time after the class. Right? We are going to use this a lot of times from today, right? When we design the systems. Okay. Now I will make this one more detailed, give you some numbers, give you A1, A2, all these numbers. So make this one. So the system is yn plus 1.5 n minus 1 plus 0.5 yn minus 2 equals xn minus xn minus 1, and the initial conditions are negative 1 equals 2 and negative 2 equals 1. Difference equation is here, initial conditions are here. What I want is try to find the output. Oh, that's nice and simple, just this one, alright? You can just A1, what is A1? A1 equals 1.5. What is A2? A2 equals 0.5 and B0 equals 1, B1 equals -1. And all these initial conditions. So you definitely can just plug into here. But I do not recommend you memorize this formula. It makes no sense at all. You can directly take the Z transform on both sides, then rearrange this, you get directly this. Does it make sense? So, but I will just use this formula here. Don't want to start from the beginning. So I'll give you the result. So the result is YZ equals negative 0.3.5 minus Z to the -1, and 1.1 plus 1.5 Z to the -1 plus 0.5 Z to the -2, and plus 1 minus Z to the -1, 1.1 plus 1.5 Z to the -1 plus 0.5 Z to the -2, then times, again, we are looking for the unit step response, the unit step response. So the input here will be 1 minus. I break this into two terms on purpose. Okay, so this corresponding to this part, which is a zero input response, and this is this term, which is a zero state response. Actually, when you do this, you may already combine these two terms, but I still suggest you break this into these two terms. Now, let's combine these two together. So that will be equal to 0.5, 1 plus 0.5 Z to the -1, then plus minus 3 on the top, 1 plus Z to the -1 on the bottom. I combine these two terms and do partial fraction expansion. I get this two. So constant A, capital A equals half, constant capital B equals -3. So you know how to do this, right? Just need some time. Okay, so now what is the output? YA. This one is 0.5 constant. This looks like an exponential, right? What is A? 0.5 or -0.5? -0.5, right? So this one is -0.5 to the n, UN. And what is this? This is UN, right? UN is supposed to be -1. This one, so this one will be -3, -1 to the n. So also an exponential, but A equals -1. Then we assume this one is a causal signal, so causal system. So that means this one, all this together with the UN, or you can just n greater than 0. Can we have 0? 0. This one equals 1. Okay, so we do have 0. Any questions? What do we call this? Complete response. Okay, now we want to examine in details what is the zero state response, what is the zero input response. We cannot start from here. We need to start from here. So this part and this term and this term. So for this term, this term here is, what is this? Which one? Zero state, zero input. Zero input, right? Input is here. So this is zero input, so zero input. And then this one here is zero state. Okay, we break the first, we do the partial fraction expansion to the first zero state. So for y, zero input, z equals negative 3.5 minus z to negative 1 on the top, on the bottom of the same. 1 plus 1.5 z to negative 1 plus 0.5 z to the negative 2. Again, you do the partial fraction expansion, and this one give us 1 plus 0.5 z to the negative 1, a plus 1 plus z to the negative 1 here, and this one here equals 1.5. This one here equals negative 5. So that means zero input response will be equal to this one 1.5 negative 0.5 n un, then plus minus 5 negative 1 to the n, and n greater or equal to 0. It's good? Alright, then the next one is y zero state will be the next term, and we break this one. So let me copy this first. This 1 plus 1.5 z to negative 1 plus 0.5 z to negative 2, then times the input this. Alright, so looks like we can cancel this term and this term. Okay? Alright, so this one will be equal to 1 plus 0.5 negative 1 plus 1 plus z to the negative 1 here. And the coefficient, this one is negative 1, this one is positive 2. So zero states, so y zero state n equals, this one is negative 0.5 n plus 2 negative 1 to the n, and n greater or equal to 0. Alright, so we have zero input response, zero state response. And we have complete response over there. Are those numbers correct? Are those results correct? Okay, we double check. We add these two. Do you get that? 1.5 negative 1, so we get half, which is here. And this one is negative 5, positive 2, so we get, add up together, get negative 3, negative 3. Okay, perfect. So those complete response, actually this term has two terms. Part 1 is due to the states, part 2 is due to the input. This one is the same thing. Any questions on this? Okay, let you give you another question. Let you think. Looks like the properties of the output signal depends on this here. So, for example, if this one is positive 2, suppose, then this definitely, with the time, this one will exponentially grows, right? if this one is a negative half, so this one decays with time. Same thing here. So this one looks like an oscillate, 1, negative 1, 1, negative 1, like this. So this one never decays to 0 or never goes to infinity. So you can see the properties for the output from this representation. So now my question is, what determines the properties of this output? How do you know that this system will decay, which means stable, right? So it will decay to 0. So after some time, because this is unit step, right? So the input is bounded. So it looks like this one is also bounded, because this one will reduce to 0. This one is just the oscillate between 3 and negative 3, right? So that means this one is also stable system. If unfortunately this one equals 2, then this one will goes to infinity. So that's not stable system. How do we know this one? So look at here. We know this is stable system. Then it depends on this term and this term. So my question is, where do this term and this term come from? Oh, it is from here and here, right? This one gives us negative half, this one gives us negative 1. Okay, so what determines this coefficient and this coefficient? Oh, that one is from here. Factorization. Okay, so that means it is from here and from here. So where does these two come from? All right, that is from here and here. So you can see, you can design a system by giving this coefficient to make this system stable or unstable. Right? For example, if your system is unstable, you can revise your system to make it stable by changing the coefficient here, to make sure those numbers are, for example, this one less than 0, or this one equal to 0. Right? If both are less than 0, less than 1, this one is equal to 1. I mean, absolute value. If both less than 1, then this exponentially decays. If equal to 1, then it's oscillate. If greater than 1, then it will exponentially increases. So you can design, if I let you, for example, I want a response of this kind, right? Then you know this term here, so you can design the system. So that's why we analyze this system from here. So you can analysis of a system is one thing, the design of the system is another thing. Usually engineers, we want to design a system. So tell you what I want. You give me the system. Right? I'll give you these terms. I want my response like like this, or like oscillator like this, or goes to infinity. Then you need to give me the system. So we need to be able to do this back and forth, analysis and design. That make sense? Okay, I will leave this here and I will remove this part. Next one, we are going to discuss frequency response. Everyone still remember what frequency response is? I mean, in analog system, when you design amplifiers or any analog systems, the frequency response. What is the frequency response? Alright, let's review something. Suppose you design a linear amplifier. I said the gain equals 10, G equals 10, with some bandwidth. For example, from 1K to 1 meg, or from 1 gig to 5G, maybe from several gigahertz. If you design the system for a 5G cellular system, so maybe several gigahertz. But anyway, the gain, or we said the A You may use A, right? Or you can use gain, Gain, equals 10 within the bandwidth. What does that mean? You analyze a lot of systems, and you also design some systems. So what does that mean? I said the gain equals 10 within the bandwidth. What does that mean? Okay, if you have this system, okay, now my input is a cosine 10t. Suppose this frequency 10 is within the bandwidth. I make it more real to 1 meg, 10 to the 6t. What is the output? The output, this is the input, the output will be equals 10 times the cosine times the input, right? Yes or no? That is the voltage gain, right? We assume. So this one, the gain times the input. That's so you may think, okay, that one will be, so the gain or the A equals, see, the output over the input. That is called the gain of the system. You may think like this, right? Okay, this one not exactly correct, right? We don't do like that. So instead, we do this as a frequency, and this one here we do frequency. So here is the frequency response. That means if the frequency, this one 10 to the 6 is within this bandwidth, then A is this. So it's only in frequency domain, the output over the input equals the gain or the transfer function here. Not really time this one. This one, why is exactly equals this? Because I said the gain equals 10. This is real. If I tell you the gain equals this with a 90 degrees, okay, then this one cannot be like this. You need to consider the angle or the phase also. But this one definitely correct. This one equals 10 with this 90 degrees. Okay, this one is good. But this one here, if you want to ignore this, you need to reconsider this one. You cannot just multiply by 10. You need to consider this angle. This 90 degrees is you will change the cosine function into a sine function. So that's different. Right? So anyway, transfer function is defined in the frequency domain. So this 10 here is the frequency response. That means if I give it 10, if you give it the input, then you just the output equals the frequency response times the input. Right? This you should know this before, but now for this class, we discuss Lrti system. Frequency response of a linear time invariant system. Suppose the input, make this discrete, equals e to the j omega n. So this is a sinusoidal function. The frequency equals omega. Always this is exponential. Recall the Euler's identity. This one is cosine omega n plus j times sin omega n. So instead of cosine and sin functions, we prefer this exponentials. Right? We already discussed the reason before, right? So I won't repeat that. So for this, suppose we know the impulse response is Hn. So what is the output? The output will be equal to the input convolute with the impulse response. Right? Now we know how to do this impulse response, right? How to do this convolution. Right? So I won't bother you how to do this. I'll just give you the result. Right? This is the input here. I remember there's a k equals negative infinity plus infinity x k times h n minus k, like this, right? Once you flip, then you shift, then you multiply, then you add. Right? So what we do, what we have here is e to the j omega n and some negative infinity to positive infinity e to the j omega k and x hk. Right? So the output equals the input convoluted with the impulse response, and we get this part. What is this? Right, that is the input. So looks like the output equals the input multiplied by some, it is constant. Right? So this k is a summation variable. So after the summation, this k will be gone. So k is not there. And omega, if you know this omega, you give me the signal, so I should be able to know the frequency. So this one is constant. So looks like this thing is constant. Right? That is called the frequency response. Right? So for this signal, and now let's record in the analog system. Suppose the frequency response for omega equals 10, when omega equals 1 meg, suppose A equals 10. Suppose omega equals 2 meg, the A equals, for example, 5. The frequency response looks like this. So this one here equals 1 meg, this one here is 2 meg, like this. Frequency response, right? You know this. So this one here equals 10, this one here equals 5. I'll give you this frequency response of the system. Now I said the input to the system equals 1 cosine 1 meg t plus 2 plus, okay, so let me make this one 10. I will just use 1. Okay, so 1 here, then plus 1, 2 times 10 to the 6t. Suppose this is the input. This is the frequency response of the system. What is the output of your system? Anyone knows this? This signal, again, we use linear property, right? Because this is a linear system. So we can calculate the response to this and the response to this, then add up together. It's called what technique we used this before in circuit analysis? You have two sources, you think only one superposition, right? And this only works for linear time constant. So now you can see everything connected, right? So we said this one is the only voltage source here. So what is the output for this voltage source here? We mentioned this at the very beginning. In this, okay. For this frequency, the gain equals 10. So what is the output? For this term?
10 cosine.
10, perfect. 10 cosine t. First term is done. Superposition to the second source, this one. What is the output for this second source? Right? Ignore this. This one is gone. What is it? It is also a gain times the input, right? So we need to find the gain for this input. Okay, what is the gain for this input? Okay, we need to look at the frequency response. The frequency here equals 2 meg. Okay, 2 meg is here. Okay, the gain equals 5. So that means for this signal, the gain equals 5. Right? The input equals 1. So the output equals 5 cosine 2 meg. So this is that. Or you cannot use 10 for both. You cannot use 5 for both. You need to separate this one because they have different frequencies. So at different frequencies, they have different gains or A. Any questions on this? Right. So we need to find the frequency response. Frequency response here is very important. Once we know that, we can easily find the output. Right? So for this input, cosine function or sine function, exponentials, for this omega, this is the gain. Means like this 10 or this 5 corresponding to this. So if I give you the impulse response, you will be able to calculate so this is called the frequency response. Any question on this? After you calculate this, you can draw this picture, right? Can you do it? Suppose I'll give you, okay, Hn equals this. Very simple. Can you draw this picture for me? Hn is here. You only need this. Then, for this frequency, you need, okay, frequency here equals 0, frequency here equals 1 mega, okay, 2 megs, and so on. You plug into there, then you calculate all this, so you get the frequency response. That is how we get frequency response from 312 or something. You know how to draw this picture, right? Yes or no? Don't look at me like that. Yes or no? See, yes. Yes, okay, yes. This is real, yes. Okay, so now I'll give you an example. Right? Suppose the system is a Lrti system. Yn equals half xn plus half xn minus 1. What this system is? You still recall when we discussed in the second chapter, when we discussed discrete systems, we have a name for this system. See? Equals input, delete input, add up together, divided by 2. What do we call this? Moving average. Does it make sense? Yes or no? Okay. Moving average. Okay, suppose the input equals, okay, 1, 2, 3, 4, so equals, this one equals Rn. Is 0 here. What is the output? The moving average means here we don't have any value. The output when n equals 1, this is 1, 2, 3, 4, so on. And what is the output at when n equals 1? It is xn plus delete by 1 time, add divided by 2. So 1 delete, so 1 and 0 equals 1, then divide by 2, so this one equals half. Yes? Okay, what is output when time equals 2? Right, that is the input at 2 plus the input at 1, then divided by 2. So which equals 1 and a half, and so on. So you can see this is a moving average. The average of this two, this is called a forward difference, or this is the sum. Okay, so this is the forward. So from, backward from here to here. So this is a causal system. You know what we are talking about, right? Causal system means when we at this time we already know all the inputs, so we can do it. So this one is very typical, very simple moving average of 2 points. We want to find the frequency response. Let's see what this looks like. Right. So this one plug into here. Okay, so this one is this. Right? We plug this one into there. So H omega equals equals this. So we need to add the infinite terms. Oh, sorry. Let's do this. Right? So this is what? This is the system. So what is Hn here? Give you this system dE. What is the impulse response? Impulse response. What is it? The impulse response It's very simple. You just replace the input with the impulse. Then the output will be the impulse response. Yes? So this one will be equal to half delta n plus half delta n minus 1. Right? Impulse response. Okay, next one we calculate the frequency response. So the frequency response is just this term. Right? Looks like we have infinite terms to add up. Look at this. How many terms do we have? 2. Okay, good. So k, we don't care of negative infinity, positive infinity. We have k equals what are the 2 terms? K equals what? 0 and 1, right? 0 and 1. Right? So when k equals 0, that one equals e to the negative j omega 0. Then what is h0? What is hk when k equals 0? Half. Right? So half. Right? Then plus k equals 1, so e to the negative j omega k equals 1, so that's here. And what is h1? Half again, right? Okay, we need to add these 2 terms together. Okay, so we need this one equals half and 1 plus e to the negative j omega. Right? We can use a little trick to do this. So this one we move e to the negative omega half outside, then this one will be half, this one e to the positive half, and this one will be negative half. Right? So use Euler's identity, and so this one will be 2 cosine half omega. Right? Then 2 cancel here. So what we have is this here equals e to the negative j omega 2, then times cosine omega over 2. Right? Okay, so this is the frequency response. For frequency response, we have amplitude response and what's the other one? You know this. I see a homework outside in the hallway. The board plot or something like all these things. And I heard you discuss in this room in 3 times. Frequency response includes 2 types. One is the amplitude response. The other one is hello? I want to hear something. Phase response? Yes or no?
Yeah.
Yes. Okay. Good. All right. Sometimes you use J, sometimes without J. Doesn't matter. Okay. There's no difference between this. Okay. The phase response, you just take the phase. Sorry, the amplitude response. So equals this. This part equals 1, right? So that will be a cosine of half equals this. Right? And the phase response just so look at this negative half j, so it's 90. So it's right. So we ignore this first. We discuss the amplitude response first. Right. So equals this. Now let's draw this. We draw the picture here. Omega equals this. When frequency equal to 0, what is the value? Trigonometry. When frequency equal to 0, what is this? 1, right? Equals 1. This looks like a cosine function, right? Okay. When omega equals pi, which equals 180 degrees, what is that? 0?
Yeah.
Yes. Okay. So that is pi. It will be 0. So in between, this is cosine function, so it looks like this. Make sense? And after that, it will be like this, but it's absolute value, so it will go up again like this. And this part supposed like this, then go up again like this. So this is 0, this is pi, this is negative pi. So this is the amplitude response. From here, recall what we just mentioned this, like this 1 m is here, 2 meg is here, so this is 10, this is 5. Now, when frequency equals to 0, the gain equals 1. When frequency equals pi, the gain equals to 0. And when frequency equals to 0, that means this is a DC. That is very low frequency, right? As low as 0, so it's DC. So DC, the gain equal to 1. What does that mean? You have a system, right? Now you record in the amplifier. The gain equals to 1 for DC. What does that mean? If I give you the input as 5 volt, what is your output? For DC, the gain equals to 1. Frequency response equal to 1. And if the input equals to 5 volt, what is your output? 5 volt. The gain equals 1. Input equals output. Make sense? Okay, now this is a very high frequency. And we assume this is the AC. Suppose the frequency is very high. For example, cosine 10 to the 6t. We assume that is very high. Then for that input, what is the output? The gain equal to 0, right? So for that frequency, for that signal, what is the output? 0. Okay, so that gives us this system. You believe this or not? Yes? Are you sure? Okay, let's check this. Suppose we mentioned yours. Okay, so I can remove all this part. I said we analyze this. So this is what kind of filter is this? Look at this. Don't look at me. Look at this. What kind of filter is this? Low frequency, high frequency.
Low pass filter.
Low pass filter. So that is a low pass filter. Means we can all pass for DC, and for very high frequency, nothing, and in between, the gain will be reduced. Right? So low frequency. Okay, now let's see. Example. So we know this is a low pass filter. Okay, suppose Xn is a unit step. 1, 1, 1, 1, 1, 1, 1. Is that DC signal? Yes or no? Is 1, 1, 1, 1, this is DC signal? Yes, right? Okay, louder, I cannot hear you. Yes?
Yes.
Yes. So what, from here, what do you expect the output is? We just said for DC, the output equals the input, right?
Yeah.
So the output also equals this. Are you sure this is correct? Look at here. Look at this. The output equals the input, then delete, okay, add, then divided by 2. So the input is 1, 1, 1, 1, 1. So the output we start from here, okay? Because we cannot start here because we don't have value yet here. So start here. This one, output here, equals this plus this divided by 2. What is it? 1. The output here equals this plus this divided by 2. What is it? 1. So you can see this is UN, this is also UN. So you have all this. What does that mean? DC or pass. DC or pass, we know that. So that is correct. Make sense? Okay, now we said for very high frequency, what is the output for very high frequency? The gain equal to this is very high frequency, pi. Why this is pi? Okay, that is related to a sampling theorem. Okay, so we don't bother you. You just need to know for pi, this means very high frequency. So for very high frequency, what is the gain? 0, right? So that means if your signal has very high frequency, then the gain must be equal to 0. Okay, I'll give you a signal. 1, negative 1, 1, negative 1, 1, negative 1. So just like this. 1, negative 1, 1, negative 1, like this. So this is a very high frequency in some sense, with some cut, okay? So with sample. This is the input. What is your output? First one from here. What is the output? Don't look at that signal. Just tell me what is the output from here, from the frequency response. 0, right? Because this is very high frequency, so the gain equal to 0. So 0 times the input must be equal to 0. Now verify by yourself. This is the system. Yes? Equal to 0 or not? Yes. At this point, the output here equals this plus this divided by 2. So negative 1, 1, nothing. Output at this time equals input plus previous input, 1, negative 1, and 0 divided by 2, 0, so nothing. So we can see there's no input at all. There's no output at all. Okay, so now we know this one is a low-pass filter. We can pass all the DC. We will cut off all the AC. So this looks like, okay, let me ask you another. What is a differential mode? What is the common mode when you design amplifier? Common mode amplifier, differential mode amplifiers. Still remember this? Huh? Yes or no? Okay. Suppose like this. Okay, let me do another. Suppose I'll give you a bunch of numbers. Okay, 1, 3, 4, 2, or something like this. These numbers. These numbers are distorted. Means we add some noise inside. The noise is a DC. It's shifted by a DC. I want you to cut off this. Remove the unwanted DC noise. So you are going to use a differential mode amplifier to do this. Okay? Or if I tell you we have an AC noise inside here, okay? So you are going to use a common mode amplifier. We discussed this all supposed to be in 3 when you discuss operational amplifiers. Okay? So now in this class we are going to use a discrete system. That means you are going to implement this with your computer. You design an algorithm like this. So if you use this system plus the moving average, what signal? We know this is a low-pass filter. So you filter out the DC component. That makes sense? Sorry, you filter out the AC component. You have the DC left. Yes? So if I give you some discrete digital signals, I said there are noise inside, AC noise. So you are going to use this algorithm to filter that out. Or if I said there are DC noise, what kind of system you are going to design? Okay? The hint is you change this one into negative. If you change this one into negative, you think, changing this in negative, that will change into a sine function, so it will be totally different. So that will be a high pass filter. Now look at this. If this is negative, if your input is DC, 1, 1, 1, 1, 1, what is your output? Zeros, right? Because you subtract each other from neighbors, so you get nothing. Means DC, all DC is gone. if you have 1, negative 1, 1, negative 1, you subtract each other, divide by 2, okay? You get 1, negative 1, 1, negative 1. You get perfect DC. So if this one is negative, that will be a high pass filter. The frequency response here will be a thin function. So we are going to stop here, and this one is up to. This is the right place to stop. So page on 148. Okay, thank you.